Hey guys, it's Mr. Sheeline here. This is going to be the video covering Unit 5.1 notes. We're going to be covering significant figures and scientific notation. Okay, so like we've been doing while we've been full remote, this has all been filled out. The only things that aren't filled out are going to be practice problems, which you need to be following along with me and answering along with this video. But there are some things in this set of notes that I do need to discuss and talk about because it is important and it's something that you have to understand before we move on. So getting right to it. So under significant figures, and we'll get to talking about what those are in just a minute. But before we get to that, we have to know the difference between an exact number and an inexact number. So what is an exact number? Well, these are numbers whose values are known exactly with no uncertainty in the amount. These are constants, and they are conversion factors. So more or less, it's these guys, exact numbers are, again, the things that we know 100% about. We know exactly how many values they have. We know the exact number of decimals that they have. These things do not change, okay? So these are exact numbers, and we use exact numbers for a number of different things. A lot of them are basic. There's quite a few of them that you use, like in calculation. So, like gravity. Gravity is a constant, more or less, is a constant. The speed of light is a constant. Things that we use, there's a thing called Planck's constant. If you were to take physics, you would learn a little bit about Planck's constant. More or less talks about electronegativity, all kinds of stuff there. But these are ideas, these are numbers that do not change because they represent a value that does not change in nature. Conversion factors are more or less just factors we use in order to convert units from one set of units to another. So it would be like a conversion factor would be an example of that would be, well, you want to change, feet to meters. So you would have to use the conversion factor or the fraction of how many meters are found in a foot and use that against the measurement of feet in order to see how many meters are in the measurement of feet that you just made. We get to that more in 5.2 notes, and it'll make a whole lot more sense when we get there, what those conversion factors are. But just keep in mind, I talk and will ask you guys about conversion factors a lot. So make sure you lock in this word and understand what that word implies. And what it implies is that it's an exact number. It does not change. And we get to why this matters in just a bit. Okay. Then we have inexact numbers. We have inexact numbers. These are basically numbers whose values have some level of uncertainty. Measurements. So if you're pouring some sort of substance into a beaker, you can get it super duper close to like 150 milliliters. Or if you're putting it on, triple balance beam or quad balance beam, you're trying to get it to 10 grams, as close as you possibly can. And you may do a really, really good job of getting it to 10 grams. And you may think that it's exactly 10 grams. But is it 10 grams? No, it's not. It could be 10.002198 grams. It could be 9.96205929786 grams. Okay, there is an near endless possibility of your measurements, things that you are physically measuring yourself, of being from one end of the spectrum to another. Okay, there's a lot of uncertainty, and you don't know if it's exactly there or not. Okay, so that's basically a good way to think of it. You've got your measurements versus conversion factors. So what do these have to do with sig figs? Well, we need to know what sig figs are first. Well, what are sig figs? Well, sig figs, and we can just write this up here. Significant figures. These are the number of values found. It's the number of values found in a measurement or calculation based upon the lowest, based upon the lowest number of values measured. So what does that mean? Well, it means, just real quick, it means this. So it means that let's say if you let's say you used one type of machine or scale to measure something. Let's say you use a scale here at the high school, and you use one of those cool little Flynn scientific ones, and they go to 2 decimal places. And you measure something out to 10.92 grams, okay? Well, here we would say, well, you've got 4 sig figs, okay, because there's 1, 2, 3, 4 sig figs. Okay, let's say you go home and you use you've got a scale in your kitchen, you use for baking, and you measure out, but you can only see that it has, it only pumps out 10. It doesn't do any decimals. But we'd say there are 2 sig figs, okay, right here. Now let's say that and so what does that have to do with either one? Well, here we have to make sure that when we're keeping sig figs, we have to go by the lowest number of sig figs. So in a calculation, and let's just say this, let's say completely look away from this. Let's say you've got a calculation where it's 10.1 times 13, okay? So we've got 3 sig figs here, we've got 2 there. So in this problem, what you should end up with at the end of the problem, you need to show 2 sig figs, because 13 has the lower number. So here would be 2 sig figs, and here would be 3 sig figs. Okay, because on your calculator, when you put that in, 10.1 times 13, it's going to give you, if you can see that, it's going to give you 131.3 for your answer. Okay, but you need to show this at 2 sig figs. So what you would do is you would go, well, 131.3, well, I need this to 2 sig figs, so I've got to round down so that it's actually 130. Okay, now we'll get to how we count those in just a bit, and we get to actually how you calculate it down at the bottom. So, but this is just to show you what we're looking at. In order to keep sig figs, you have to keep the lowest number, because you want to be as accurate as the tools that you're using. You don't want to overinflate how accurate a particular tool is, because if you do that, your calculations will be off. If your calculations are off, your measurements are off. If your measurements are off, your conclusions about a particular question are going to be off. They're going to be wrong. Okay, they have to be as accurate as possible and as accurate as the machines you're using. Okay. So let's get more into counting the sig fig. Oh, and sorry, by the way, before that, to know the exact versus inexact numbers. So let's say in this problem here, let's say that actually, or let's say this. Let's say that in a problem, you're wanting to, I don't know, let's say you're multiplying 10, and let's say 10 is an exact number, and we're going to multiply that against your measurement. And your measurement is going to be, let's just say it's 24.69, I don't know. So if this is an exact number, and this guy right here, this is your measurement, so it is an inexact number. Okay, so when you're multiplying these against one another, we do not count the number of sig figs for exact numbers. So the answer here, if you pop that in your calculator if you need to, okay, so your answer here, 246.9, it's good to go like this. Okay, we've got 4 sig figs here. We've got 4 sig figs here. Okay, we do not count the number of sig figs from exact numbers. And we'll continue practicing this, especially in Unit 5.2. So it's just and if I'm confusing you further and boring you super out right now, I apologize, but this is stuff you need to know and stuff you really got to lock in. Okay, So again, exact numbers, we do not use those guys when we're counting sig figs. Inexact numbers, that's what we use to count sig figs. Okay, so the question has to be, how do you count sig figs? Okay, so the first question that you need to ask yourself, is there a decimal in the number? If yes, you start counting from the left. If no, you start counting from the right. Okay. Now here's the thing though, for both of them, do not start counting until you hit a non-zero digit. So that's basically just 1 through 9. So let's say, and we'll go through those examples down here. And then number 3, once you start counting, you do not stop. So even if you then hit a 0, you don't stop counting. You count the 0 if it's surrounded by, non-zero numbers. Okay. So that'll make sense when we look down here. Now, this point right here, so this is a reminder, and we kind of talked about it up here when we were more or less defining what a sig fig is. You want to be as accurate as your least accurate measurement, or as accurate as the least accurate measurements made by the least accurate machine or tool. So it's to say like a Barbie versus NASA scale. So this is an example you'll find online all the time. Okay, a NASA scale, let's say the NASA scale, NASA scale can measure, let's say, 100 decimal places. Okay, but the Barbie scale can only measure to 1 decimal place. Okay. So if you were to use the measurements from your Barbie scale and try to use them with your NASA, you'd have to make sure that all of your NASA, and that's a bad one. Let's say instead of 1 decimal place, it's not 1 decimal place, but let's say it can only measure to 3 sig figs. Sorry, let's say this can only measure to 3 sig figs, and this can measure to 100 sig figs. Not decimal places. I don't want to confuse you there. So if the Barbie only can measure to 3 sig figs while the NASA can measure to 100 sig figs, we would have to use the number of sig figs from the Barbie in place of the NASA if we had to use both measurements in a particular number of calculations. Because again, you don't want to say that the Barbie scale is as accurate as the NASA scale. And I'll be reusing this analogy over and over and over again, and hopefully at some point it will make sense. Again, if you want to be as accurate as possible, now I'm not saying to try to justify yourself as correctly as possible. It's admitting that your tools you're using are inaccurate and that the measurements you got were based upon these tools. You do not want to say that your inadequate material, your inadequate measurements are as adequate and as accurate as ones that are like far superior. Okay. Because your measurements will be off, and again, you don't want to make it seem like a Barbie scale that can only measure to 3 sig figs is as accurate and as good as the NASA scale, which measures to 100. Now that sucks if you use a NASA scale, yeah, that you've got this super duper specific and super duper precise and accurate measurement with the NASA scale, but you've got to then follow with the number of sig figs found from your least accurate measurement. So again, if these had to be combined, you'd be left with numbers that only have 3 sig figs. Okay. So again, we'll continue practicing this. I'll continue, trying to make sure you guys understand what that means, how that affects your numbers throughout Unit 5 and beyond. Okay. So practice. Okay. So all we got to do here, we've got to count the number of sig figs in these numbers. Okay, so remember these questions up here, okay? Questions and prompts, I should say, So let's just ask that first question. Is there a decimal? So for number 2, or for this number here, for number 2, no. So we got to count from the right. Well, thank God there's only one thing here, so this one's pretty easy. There is 1 sig fig here. Okay. All right, now for the next one, well, this guy does have this one does have a decimal, so we got to start from the left. So we start right here, and we're going to count from left to right. Okay. Now, Number 2 here says, though, we do not start counting until we hit a non-zero digit. Well, the first thing we hit here is a non-zero digit. So we do not count this one, but we do count this one, and we do count this one. So 0.62 has 2 sig figs. Okay. So the next one, okay, again, we do have a decimal, so we start from the left and we work to the right. Here we do have a 1, so we do count this one, so that's 1, 2, 3. So 3 sig figs. This next one, we have 3,000. Okay, well, 3,000 here, we don't have a decimal here, so we're going to start right here. Okay, and we count from right to left. Now, again, we don't start counting until we hit a non-zero digit. Well, we can't count that one, can't count that one, cannot count that one, but we can count that guy. So this 3,000 has only 1 sig fig. Okay, do repeat here. Nope, 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 and then yes, 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 yes. So we've got 4 sig figs here. Same thing down here. We've got 1, 2, 3, 4, 5, 6. We have 6 here. So remember, once you start counting, you do not stop. So yeah, we don't count this guy. We don't count these 4. Oops. We don't count these 4. But as soon as we hit that 5, everything from the 5 over, we count. Okay, so we count the 5, the 3, the 0, the 8, the 0, the 0, which will give us 6 sig figs. Okay, let's try to look at this guy. So we're going to start here because it doesn't have a decimal. Can't count him. Nope. Nope. But we can count this guy, we can count this guy, and we can count that guy. So there are 3 sig figs. Okay. Decimal. Start here. We can count that guy, we count that guy, and we count that guy. There are 3 sig figs. Now, why do we count those zeros? Because it has decimals, so we count from left to right. And since it starts with a 4, we start counting and we don't stop. So that counts, that counts, that counts. Okay. Now, try those 3 on your own. So pause the video real quick. Try those on your own. And then once you got them, play the video again, and then I'll just show you the answer. Okay. So looking at these 3, because these 2 are a little tricky, should be a little tricky. This guy, maybe we don't know exactly what to do with that guy. So 300 here, there's no decimal, so we start counting from here. Don't count that one, we don't count that one, but we do count this guy. So we do have 1 sig fig. We have a decimal, so we start at the 3, so that's 1, and then we don't stop. So we count from left to right. Or sorry, this one should have been, or no, yeah, this one should have been, yeah, we count from left to right. So 1, 2, 3, we have 3 sig figs. So why do we have 3 sig figs? Because of that decimal. The decimal tells us that it is very important that we have these 3 digits here in order to show, and to maintain that number of sig figs. This last one is in scientific notation. So here, all we care about are these 3. Okay, it's a decimal, it is a fraction in this case, or at least the way it's set up right now. So we do count these guys. So we see there's a decimal, so we count from left to right, everything that's a non-zero, and then beyond. So 1, 2, 3. Now, why don't we count this guy? That's just because this guy just tells us the size of the number. It was to shorten it up, and that we'll get to that in just a second. It's again in scientific notation. Okay, so I know this video is kind of long right now, so let's just keep on trucking though. If you do need to take a break, make sure that you pause the video, come back to it, whatever you need to do, but we're going to keep on trucking. So adding and subtracting sig figs and calculations. Excuse me. So adding and subtracting. So when you're adding and subtracting, which we don't do a whole lot in here, you do a little bit in Chem 2 where it's a bit more important. So we'll talk about it, but realistically speaking, most of the calculations that we do, if not like all the calculations we do, are going to be multiplying and dividing. However, it's still important to talk about, adding and subtracting and all that good stuff here. So just to go through it and just so you understand what it is. So when we add and subtract, you just casually do what you normally do. You add or subtract. You just go through the motions. You do the math. Okay, then 2. You find the estimated, the furthest right, sig figure for each measurement, specifically the inexact numbers in the problem. And then you round the answer to the least specific, the furthest left placeholder of the estimated digit spots. So again, and I can't remember if I don't think I have an example. Yeah, I don't have examples of that in here. So in this case, this is more about decimal places than it is actually about sig figs, though it does also affect without, if you don't have decimal places. So round the answer to the least specific or the furthest left placeholder of the estimated digit spots. Again, we don't really go over this. We don't practice this. We practice multiplication and division, which is way easier. But just, again, so you know what you do here. And there will be some extra credit, just so you're aware. There will be some extra credit questions that do have you work on this. So just keep that in mind, okay? So if you want further, if you want to further practice this, easily just Google adding, subtracting with sig figs, and you can practice online, because again, what I want to focus more on is just multiplication and division, okay? Now, multiplication and division is way easier, and it does sound kind of the same, but it's not the same. When multiplying and dividing, you do the math, you multiply and divide, you count the number of sig figs, significant figures, for each inexact number, your measurements, and then you round your answer so that the same number of sig figs as the smallest number of sig figs from the inexact numbers, okay? So that was like the problem that we did on the front there. So when you're multiplying and dividing, so if this is an exact number, this 10 is an exact number, while this 24.69 is inexact, we only focus in on the inexact number, or the inexact number of sig figs here. Now, if both of them are inexact numbers like this one right here, we have 10.1 times 13. There's 3 sig figs here. There's 2 sig figs there. So our end answer, after we multiply and do the math, we need to make sure that we either will round up or will round down, and so that we have 2 sig figs. Now, being sophomores, juniors, and seniors, we should know what rounding up and rounding down is. If you still need help on that, make sure you get a hold of me so that you know what to do, know what to expect when you're rounding up or you're rounding down, okay? So again, get a hold of me if you still need to practice that. Okay. Now, this one is a little bit easier to just grasp, so I won't really go through scientific notation other than just talking about what it is. You can read this on your own. It's a lot easier than remembering sig figs, or at least that's what my students have showed me from last year and what Mr. Hamers talked about with me. So scientific notation, what you need to know about that, this is a method of writing very large or very small numbers a little bit more easily, or expressing them to be a little, I guess, cleaner looking. And it looks a little intimidating, but realistically speaking, it's nothing, okay? So I guess I will just quickly go through these ideas here when you're putting them in and when you're taking them out of scientific notation. So when we're putting a number into scientific notation, the beginning portion number has to be between 1 and 10. Okay, so meaning that you can't have, you want to have a decimal that has a ones place but no tens place. Okay, so it'll be like 1.623. It'll be 2 point something. It'll be a number, point, and then whatever is afterwards. Okay, so just it has to be between 1 and 10, the first number. Okay, realistically speaking, there should be 1 and 9. Okay, can't be 10. The second part is a power of 10, so that's times 10 with an exponent. Okay, So when putting a number into correct scientific notation, remember LARS. So left you add, right you subtract for your decimal movement. So when you're moving the decimal to the left, you're adding to the exponent. When you're moving the decimal to the right, you're subtracting the exponent. Okay. So let's just practice that real quick. So we're going to put these numbers in scientific notation. So we've got a big boy number here. We've got 450 million. We want to put that into correct scientific notation. So what we need to do, find out where the decimal is. So in this big boy number, and because there's no decimal shown, we know that the decimal is going to be all the way to the right at the end of the value. There's our decimal. And where that guy has to go, it has to go between the 4 and the 5. Okay, because again, that first number has to be between 1 and 10. 45 is not between 1 and 10. Okay, so it has to be between it. So what we're going to do is we're going to move this decimal to the left, and we're going to, and because it's going to the left, we're going to be adding the numbers. So here we go: 1, 2, 3, 4, 5, 6, 7, 8. So our final answer here would be 4.5 times 10 to the 8th power. Okay, 4.5 times 10 to the 8th. It's as easy as that. Okay, let's look at this next one. Well, this next one has a decimal already put in for us. It's right there. But this time we're going to go to the right. As it says here, when we're moving to the right, we're going to subtract. So here we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, the question is, Mr. Sheline, why did you stop after the 8? Because remember, your first number, so like this decimal that I made up here, this 4.5, the first number has to be between 1 and 10. If I were to go one more space to the right, it would be 80.1. Is 80.1 between 1 and 10? No. Or I should say, is 80 between 1 and 10? It's not. 8 is between 1 and 10. Okay, and so here, I've already forgotten how many jumps we had. We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here, our answer would be 8.01 times 10. Now, because we went to the right and we were subtracting, you could say that you subtracted 10 from 0. Another way to think of it, when you move to the right, you're making a negative number. So we moved 10 to the right, so that means that we have a negative 10 exponent. So our final answer here is 8.01 times 10 to the negative 10th power. Okay. Try this guy. It's right here, so we're going to move it 1, 2. So we've got 4.7205 times 10 to the second power. Okay. Easy peasy. This guy, decimal's right there, so we're going to go 1, 2, 3, 4. So then it's 9.6. Now we keep that 0. Okay. Now we don't keep these zeros, but we want to keep this 0 right here, because remember, this is part of keeping sig figs. Is that if we've got, because here 0.000960, there are 3 sig figs. So if there are 3 sig figs there, we've got to make sure we keep those. So it'd be 9.60 times 10 to the 1, 2, 3, 4, negative 4, fourth power. Okay, so let's keep on trucking. Now, this guy may look like it's already in scientific notation, but it's not. And this is really where that Lars is going to come in here. So 2,670, is that between 1 and 10? No. How can we get it between 1 and 10? Well, we're going to find the decimal, which is right there, and we're going to move that decimal to the left. So we're going to move it 1, 2, 3. So now the answer is going to be 2.670 times 10, but to the what? So we move the decimal left 3 spaces. There's already an exponent here, so we're looking at Lars, since we move it to the left, we are going to add. So our final answer here is going to be 2.670 times 10 to the 9th power, because it's just 6 plus 3. Okay. And then for f, again, we may think it's already in scientific notation, but it's not. So here's our decimal, and we've got to move it there between the 3 and the 5. So we're going to go move it 1, 2, 3 places. And so again, we have a, it's already in some kind of scientific notation, but not correct scientific notation, so it already has an exponent. Because we move to the right, we're going to subtract 3 from negative 3. So we're going to have 3.5 times 10 to the negative 6th. How do we know that? Because negative 3 minus 3 is negative 6. Okay. For g, 10 to the negative 8, this is where where you could do it two ways, but because we're just putting it into scientific notation, we've got to put the decimal where it belongs, figure out where that's at, and then we have to move everything accordingly. So we're going to move that decimal to the left because it needs to be between the 7 and the 6. So it's going to be 1, 2, 3, 4. And because we moved it 4 to the left, that means we add. So it'll be 7.6 times 10, negative 8 plus 4. It's negative 4. Okay. And then finally, here at h, find that decimal, and we got to move it between the 3 and the 8. So we're going to go 1, 2, 3, 4, 5, 6, and that's 6 to the right. So we're going to end up with 3.84 times 10, and this was, again, 6 to the right, so 3 minus 6. So 3 minus 6 is going to give us negative 3. So that's how we put numbers into scientific notation. Okay. So why is scientific notation important? Scientific notation is important because it allows us to take super big numbers like 450 million, and we can put them into simpler numbers down here. And this is probably something you've already seen your calculators make. So especially like your smaller scientific calculators and also your graphing calculators too. But you probably have seen this. So if you're adding or multiplying really, really big numbers, as an example, maybe you've seen something like this. You'll see 4.5 E8 like this. Okay, you've probably seen that before. This is exactly the same thing as this. Okay, that E in your calculator is equal to times 10. Okay, which you should already know this, but in the case that you have forgotten, here's a reminder. So anytime that you have plopped in something that's like a super duper huge number in your calculator, and then your calculator spits something out looking like this with that little E and then the exponent, all that means is this. This is equal to saying 4.5 times 10 to the 8th power. Okay, I just shorten it up by making the E to mean times 10. So you've already seen this before. You probably worked with it already before. Should have worked with it already before. Okay. So here's a basically double reminder, more or less, to remind you, hey, you have worked with this before. Also, here's another way, and probably the way that your calculator has shown that to you. Okay. So again, if you need a quick break, make sure you take a quick break. But I'm going to keep on trucking. Remember, you can pause it here, whatever you need to do. But this is the last thing in the notes that we're going to cover. And this is taking things out of scientific notation. So taking things out. So if your exponent is negative, move your decimal place to the left, the same number of spaces as the number in the exponent. If it's positive, move the decimal to the right, the same number of spaces as the number in the exponent. Okay, so just to practice that, which seems pretty easy. So 5.02 times 10 to the 7th power. So what we're doing is we're going to take this dude and we're going to move it to the right because it is a positive exponent 7 times. So 1, 2, 3, 4, 5, 6, 7. So it's going to be 1, 2, 3, 4, 5 zeros we're adding to this. So it'll be 5.02. 1, 2, 3, 4, 5. add some commas in there. So 5.02 times 10 to the 7th power is actually 50,200,000. Okay, so we just took that out of scientific notation. Let's try another example here. So it's going to be 9.224 times 10 to the negative 4th power. So we're going to grab the decimal here, and we're going to move this guy four decimal places to the left. Why? Because it's a negative 4. So we have to, this is going to be a decimal. It's originally like a pretty small decimal here. Okay, so we're going to move it 1, 2, 3, 4, and we're going to plop in all those zeros. Don't forget the very first one. So it's going to be 0.00, and how many is that? It's 3 zeros. 9224. Okay. And then here, 4.609 times 10 to the 2nd power. Grab that decimal, positive, so we're going to go to the right this time. So 1, 2. So then we actually have 460.9 for our final answer. And then last but not least, 7.7 times 10 to the negative 6th. Because it's a negative exponent, we're going to be moving the decimal to the left. Okay, so grab it. And then 1, 2, 3, 4, 5, 6. So that's 1, 2, 3, 4, 5. So 0.123457. Easy peasy. Okay. Now, this set of notes covered a whole lot of, not so much new stuff, but a good number of things that I spoke about verbally that I didn't have written down. And that I did write down, and some things I said that I obviously didn't have written down, all that good stuff. So, and this is a lot of important material. So make sure that if there's something you didn't understand about this, make sure you go back, rewatch, the portions of the video that you need to, whatever you need to do in order to understand all this good stuff. If you still don't get it watching the videos, remember, during full remote, I do have office hours for you guys. I pretty much have office hours all day. I give the links out to everybody. You can join in whenever you want. Typically, though, for chemistry, you guys have it later in the day. I believe it's 1:30. Oh shoot! On Tuesdays and Thursdays, I believe it's like. Oh no, I'm blanking out on what it's supposed to be. I have the schedule up on my Google Classroom. I don't have access to it at this very second, but I do have it in late in the day. Remember, I'll post about virtual office hours again on Tuesdays and Thursdays. Saying, hey, ask if you need to. But point is, make sure you come to those virtual office hours. Ask me questions. Make sure you understand the material that we're working on. Okay. Because again, we talked about a lot of stuff. We talked about sig figs, and you've got to know what sig figs are. I can tell you that from last year, I had more kids struggle with sig figs than I did scientific notation. Okay, that's why I pair them up. Is that scientific notation at the beginning? Yeah, there's some bumps in the road, but you guys get it. It's sig figs that we have a real tough time understanding and remembering while we're doing all of our calculations. Okay, because we need to keep sig figs as we do these calculations. So if you still have questions, make sure you ask me. Make sure you come to those office hours. You can text me on Remind. You can email me. You can ask a question through comments on Google Classroom. There's too many ways to get a hold of me, and there's too many ways to get a hold of me. And there's very few excuses why not to get a hold of me if there's something you don't understand. Okay, so that will wrap up for the notes. And again, I know this is a pretty long video for the notes. So thanks for sticking with me. Hopefully this was helpful. Just keep an eye out for all the posts that I'll be making with all of the homework and all that good stuff that you need to complete as we go through the full remote until we come back to do hybrid. Okay. All right, guys. Well, that's it. So thank you for watching. If you have any questions, make sure you get a hold of me.